Hi everyone, Mr. Mahadi here. Going to make this video to help you out with the second part of part 2 if you were gone or if you just want to look back at what we did in class today. So we're going to break down the two different boundaries and look at them in terms of convection, draw some arrows, and make sure that we're all on the same page about what convergent, divergent looks like on the surface and beneath the surface. So let's start with convergent boundary, and we know that if it is converging, that means that it's coming together. So I would draw those arrows above just so you know where exactly those plates are going. And then on the other side, divergent boundaries, that means it is diverging or dividing and going in different directions. So those are the motion of the plates, which is really important that we know that because that's going to help us draw our convection currents. So just like you did up here, you can see, like in image 3, you can see the direction of the plates, and that'll help us draw our convection currents. So since we have two plates, I should have two convection currents here. And I know that since they're coming together, I'm going to start with the convergent boundaries. I know that this slab right here needs to be moving down to the right. So I know that's where my convergent, or where my convection current should be going. So I know that my warm always starts at the bottom because that's where it's closest to the inner core. So I'm going to draw an arrow up here for my warm, knowing that it comes from down here. This is all the warm stuff down here. Warmer parts of the mantle that are convecting up themselves from the outer core and inner core. And then as my mantle gets far away from this warm area, it's going to travel and grab that plate and move it all the way down. So you have to make sure your current goes up and shows that, yeah, that mantle is actually grabbing this part of the convergent boundary and dragging it down with it. It's pulling it down with it. And then finally, my other blue arrow goes to show that it's cool until it gets to the warm spot again, and we could draw a small hot arrow right there. And that's what our convection would look like on the left side. Now, the exact same thing except a mirror image on the right side. So we know that this crust is moving to the left. So that means that my warm arrow should be up and moving to the left because it's going to be dragging that continental plate into that other convergent plate. So then I can switch to blue, and I'm going to show it going all the way into this other one, pulling down. It's going to be, that wasn't very good. It's going to be warming up right here and finishing our current like that. So the warm comes up, gets far away from that hot part of the mantle, and then it comes down on the other side, and it's dragging that plate with it. It's dragging, pulling that plate with it, crashing into the other one, and then it's going to heat back up and keep going. So that's what our convection would look like for our convergent boundary. Now let's draw it for our divergent boundary. So we know that this plate is moving to the left and this plate is moving to the right. So our warm needs to come up and start pushing that plate to the left. Needs to start separating it out, and then we can draw our cool arrow pulling it that way because it's got to be pulling it to the left. And we know from our convection lab that cool stuff sinks. It's going to heat back up from this warm area down here, the warm mantle down here. It's going to heat back up, go up to the top, pushing to the left, and then sinking back down to start the process over again. Now, again, we have a mirror image, starting up in the warm and pushing to the right this time. Right at that ridge, it's going to start pushing to the right. And then we know as it gets far away, it's going to push all the way over there, start to sink down. That cool mantle sinks down, then all of a sudden, whoops, it's by the warm stuff, it's going to heat back up again. So those are what our convection currents would look like for convergent and divergent boundaries. So right now is the time you need to pause and kind of do a self-assessment. Can I do that by myself? if my teacher just handed me a random boundary and said, draw the convection currents, do you think I could do that? If you can't, either go back and start the video over and watch it again, or you need to talk to your teacher, because this is super, 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 super important that we understand how these convection currents match up with the plate boundaries. And you can always test it, because you can see this arrow right here is going to the right, should be the same as the direction of our plates. This arrow here is going to the left, should be the same direction as our plate motion. So you can always check yourself there. All right, description of plate motion, together or apart. Well, this one's pretty easy, because we know that the convergent boundaries are coming together, so we would say together for this one. And we can see that the plate motion is very obviously going apart for our divergent boundary, so we would put apart in for that one. And then name and describe force. Okay, so we need to be thinking about the force which is happening at both of these. Now, I used the language when I was describing it earlier, but since these plates are getting crashed into each other, this part of the subducting plate right here is getting pulled and pulled and pulled farther into the mantle. So you can see these two arrows right here are pulling that plate down. It's literally yanking that plate down into the mantle. Okay, so we know that it has to be getting pulled into the mantle. So this would be our slab pull. And then if we went over to the divergent side, we can go and we see that these plates are actually pushing it apart. If you remember the demos in class of being pushed apart, coming up here and being pushed away from each other, they're literally being separated, they're being pushed. And we know that this is our mid-ocean ridge right here, right? So if this is our ridge and it's being pushed apart, we would call this ridge push. Ridge push. So in slab pull, that subducting plate is getting pulled down into the mantle. So we can write that. Subducting plate is getting pulled into the mantle. Because that plate is literally getting pulled down by gravity and by these convection currents. It's like tug of war. It's being pulled down into the earth. And then on the other side, ridge push, well, the magma at the ridge, so this usually occurs at like a mid-ocean ridge, magma at the ridge is pushing older crust away. So this new magma is coming up and pushing that older stuff away, coming up and pushing that older stuff away. So ridge push always happens at the mid-ocean ridge. Slab pull always happens when this slab is getting pulled down into the earth. So pull, you can think pulled down into the earth. Push, you can say pushed out on top of the earth. And then looking down at this question down here, this is a try it on your own. So after I've talked about all of these things and you have these notes, you can go back up and look at these while you're filling this out. But do your best to name both boundaries at the green star and at the orange star, and then label the motion of the plates. There's a hint on there if you look closely. And then you need to draw the convection cells. Okay? Remember, there should be 2 convection cells for each boundary, like I have up here. 2 convection cells for each boundary. Okay? After you're done, go hit up learning target number 8, get it done. And if you're confused about any of this, it's a tricky topic, please send a message to your teacher if you're gone, or talk to us the next day in class, because we want to make sure everyone's got convection down. All right? Thanks for watching.